But now I would like to talk about sets, right? So what are sets? So this is more or less the basic mathematical object, right? So what could be easier than a set? So this is when you even start talking about mathematics, so the very basic definition is about sets. So it even precedes numbers, right? So really there could be nothing more basic and more primitive than this, right? And sets themselves, well, of course they appear everywhere, right? So you can think of everything as a set. It's some sort of, you can think of a geometric object with the least structure, right? And they can themselves be important on their own, right? So if you can think of three-dimensional point clouds, right? So this is how often you capture information, right? So this is part of reconstruction of Oxford. So it's a point cloud. So this is what you get from a drone, for example, or from a range scanner or LiDAR. So you get basically sets where the elements are the x, y, z coordinates of a point and maybe some extra information like color, right? So often you have six-dimensional points, x, y, z, r, g, and b, right? So that's exactly what you see here, right? So this is, every point here has three-dimensional coordinates and also three-dimensional color coordinates, right? So that's what it is. You might also have some other information like normals, right? So basically you get some kind of idea about orientation, right? About local geometry, but that's the simplest thing, right? One thing that you need to understand, this is really the key characteristic of sets, and we'll see it also with graphs, is that you don't have a natural order, right? So the elements come unordered. It doesn't matter if it's first element A and then element B or the other way around. You don't have a way to establish this order in most cases, right? And we'll see that most of these conclusions that we'll make about sets, right, and the design of algorithms that we will make for learning on sets will naturally carry over to graphs. That we'll see in Ismail's lecture next. Okay, so what do we want essentially when we deal with sets? So we have a function that takes as input a set, right? So I want, for example, to classify a point cloud, right? Let's say this is my task. What I want to make sure is that basically this natural symmetry, right? So the idea that I cannot order naturally the elements in a set, it's kind of built in the definition of this function, right? So I don't want my function to be sensitive to the order of the elements in the set because I don't have this order. So I want basically this to be achieved by design. Okay, so let's define it more formally. So we have a domain which is just index of numbers, right, from 1 to n, right? So these are the elements of the set. And then the signals, right? So we have some vectors in Rd, right? That are again indexed from 1 to n, right? So this is our set. And we have a label function that takes a set and produces some output, right? So something like this, right? So we want this function to be permutation invariant, right? In other words, for any order of the elements in the set, I want the output to be the same, right? So this is permutation invariance, right? So we already now encounter for the first time this notion of symmetry, right? So now this the symmetry is the permutation group, right? And the property that we want is to be able to forget about the order of elements in the set, okay? So let me just make it slightly more convenient. So I would like to arrange the elements of the set into a matrix, right? So I assume that the elements of the set come from the same universe, right? So they're all d-dimensional vectors, so I can represent them as a matrix of size n by d, right? N is the number of elements, and d is the dimensionality of the feature vectors, okay? And now I have the label function is a function that takes a matrix of size n by d and produces some label, okay? So I can write it like this. So I can write it in matrix notation, f of px equals f of x, right? What is p? P is a permutation matrix, right? So it's a matrix that permutes the rows of this matrix representation of the set, right? So it acts on the matrix X from the left, right? And it changes the rows. Now I can also have basically an equivariant version of this function. In case of equivariance, my output has the same structure as the input, right? So I input a matrix, I produce another matrix, possibly of different dimensionality, right? So I started with a set of n d-dimensional element, I produce a set of and d prime dimensional elements, right? Like shown here. What I want to make sure is that if I permute the input, the output will be permuted in the same way, right? Something like this, okay? So mathematically, the way to write it is that f of px, right? And f here, the output is a matrix, so that's why I use the bold uppercase notation to say that the output is a matrix, is the same up to permutation, right? So said differently, f commutes with the permutation, right? So I can first permute and then apply f, or I can first apply f and then apply the permutation. The result will be the same, okay? So how does this matrix look like? So these are matrices which have ones, only a single one in each row, right? And basically these are permutation matrices. So this is representation of the permutation group, right? I can represent the permutation group like this, right? And it's exactly one single one in every row and every column. They are bistochastic, meaning that the sum of rows and columns is 1, and they're also orthogonal, right? P transpose P equals P, P transpose equals I. And they're also non-negative, right? So the elements are either 0 or 1, okay? So basically, permutation matrices are orthogonal, bistochastic, non-negative, right? They have all these properties. And we have, of course, n factorial possible permutations. So it's a very large group. So it grows exponentially fast. Okay, so the question is, how do we do the learning, right? So let's start with a very simple case, right? So we are interested in functions of sets of this linear form, right? So I give you a set again in this matrix representation, right? Again, I will need to account for the fact that the rows are ordered arbitrarily, so we'll see it in a second. So my matrix looks like this. So I multiply x from the right by some matrix W. So basically this multiplication from the right by the matrix W means that I act on every element in the set independently, right? Again, each row in this matrix represents an element in the set, right? So when I multiply from the right by W, it means that each row is transformed independently in the same way, right? By the same coefficients W, right? Sometimes we call this channel mixing, right? So each element transformed in the same way. And then we have the matrix theta that multiplies from the left. So it's of size n by n, right? So this is what mixes the elements of the set, right? And now the question is how these thetas must look like if we want this function to be permutation equivariant, right? And the theorem here is an if and only if statement, so we'll prove both directions, is that it must be either identity or the matrix of ones, right? So in other words, I can either consider each element on its own or all the elements in the same way, right? So I can either average everything or consider each element on its own, right? So that's the identity and the matrix of ones, right? So the one outer product with one transpose is just a matrix of ones, right? Over n, so to make sure that it's matrix of ones, okay? So let's prove it in first direction, right? So first of all, we can see that we can ignore W, right? Because it doesn't do anything to the set, right? So it multiplies each element in the set independently, so I can just absorb it into the x, right? So if I multiply by W, I can call it the new x, okay? So it doesn't change anything. Okay, so I can ignore it. Then first we can check that if we have two thetas, right? So this is the conjecture in this theorem. So theta 1 is I and theta 2 is the matrix of ones. So first of all, I, right, doesn't do anything, right? So if I multiply it by a permutation matrix, it's still the same permutation matrix, right? So basically that has no effect. What about theta 2? So theta 2 is matrix of ones. If I multiply it by permutation matrix, it's all ones, no matter how I permute it, it's still all ones, right? So you see that in both cases, I get invariance, right? And the linear combination obviously satisfies the same property, right? So basically, equivariance is satisfied automatically. Now, what about the opposite direction, right? So let's assume that I have a matrix theta that is permutation equivariant, right? So in other words, p theta equals theta p, right? Or in other words, I can say it's p theta p transpose equals theta, right? I can multiply by P transpose on the right-hand side, right? And this must hold for every P, right? So all permutations, okay? And now let's see how this theta looks like, okay? So let's first consider the element on the diagonal of this theta, right? So let's call it theta I, right? So if I do a permutation, the P permutes the rows and the columns. Let's say I becomes an I prime, right? So this element I becomes I prime, right? So it's an element on the diagonal, right? This is true for any permutation. So any permutation of I into an arbitrary I prime, this must hold, right? So what does it tell about the diagonal of this matrix? That all the elements on the diagonal must be the same, right? Again, this is for all permutations, right? So from the property of equivariance, right, I chose an element on the diagonal. I see that all the elements on the diagonal must be the same, okay? What about another element? So let's pick up an element outside of the diagonal. So let's pick up an element ij where I is not equal to j, right? Then we have the permutation permutes I and j into some other indices. Let's call them I prime and j prime, right? So this element ij becomes some I prime, j prime, right? So one off-diagonal element into another off-diagonal element, right? Again, this is true for any permutation. So any change of index of I to I prime and j to j prime must be the case, right? Because we assume the equivariance, right? So in other words, p theta equals to theta p. All these elements must be the same, right? So basically the conclusion is that we have all the elements on the diagonal the same and all the elements outside of the diagonal are the same, right? So this is exactly this, right? So we have these two possible matrices I, right? So that's the matrix, the diagonal matrix, right? So it gives us the element of the set itself, or the matrix of ones, which is basically everything else, right? So in other words, in a set, as I said, you can do only two things. You can either consider yourself, or you can consider everybody together, right? So I can either sum up everybody, right? I cannot distinguish between elements. So I can either do an operation with the entire set, or I do an operation only individually with each element, right? There is no other option, okay? So again, this is the linear case. Now, what can we do in the general case? So in the general case, we'll see an architecture, but first maybe let's make a theoretical statement. And this statement is about universal approximation, right? So remember, universal approximation was important for general neural networks, for multi-layer perceptrons. We've seen that with just 2 layers, I can approximate any arbitrary function to any desired accuracy, okay? So here we have a different situation. We are not interested in just any function. We're interested in a permutation invariant function, right? So I want universal approximation results for permutation invariant functions. So the result is like this. So we have a set, right, X, that is taken from some compact subset of RD, right? So compactness is required for the theorem to work, right? But basically we're talking about elements in a d-dimensional, elements of a set drawn from d-dimensional space. Then for every continuous permutation invariant function f, right, like this, and epsilon greater than 0, there exist suitable functions, let's call them phi and psi, such that this approximation error, right, between f and this thing that we'll explain in a second is bounded by epsilon, right? So in other words, any permutation invariant function f can be approximated to any desired accuracy epsilon by something that looks like this, right? So what is this thing? You can see two things here, right? So first of all, we have some function psi that is shared. It operates on every element of the set, right? So I have the same function that first applies to every element of the set. Then I sum everything up, right? And then I apply some other function, right? First of all, you see that by construction, this is permutation invariant, right? So I first operate independently on all the elements of the set, and then I sum, right? So sum is permutation invariant function. I don't care about the order, right? So the elements of the set here come in arbitrary order. Doesn't matter in which order I sum the elements, right? The result will be the same, okay? So here are some subtleties. First of all, when we say about continuous functions on sets, we need to understand in what sense we understand continuity. So the correct way to define it is we need to define a distance between sets. So this is called the Hausdorff distance. we also can reproduce these results with other types of aggregators. Instead of sum, we can take any other permutation invariant function, like a maximum, for example, right? So there is a version for maximum as well. And now, remember I mentioned this Kolmogorov-Arnold approximation. So this was the earliest universal approximation results from the 50s. So basically what it says is that if I give you an n-variant function like this, f of x1 through xn, not permutation invariant, right? So the order of the arguments here is important. It can be approximated like this. So as univariate functions applied to each of the coordinate of the input, summed up and then fed into another nonlinear function. But here we also have coordinate dependent coefficients, alpha I, right? So in Kolmogorov-Arnold approximation, these alphas are important because coordinate order matters. In our case, coordinates, right, or the position of the element in the set do not matter because we don't have this order, right? So that's why we don't have these alpha i's, right? So it looks like Kolmogorov-Arnold theorem, but we don't have these alphas, okay? So if you look at this architecture, basically it does two things. Again, it is independent processing of each element in the set, right? So this is this function psi that is shared. So that transforms each vector independently. And then we have a permutation invariant. So this is permutation equivariant, right? So if I change my order of the inputs, the outputs will change in the same way, right? And then we have a permutation invariant aggregation, right? So we have this function that, for example, a sum or a maximum, right? That aggregates them together and applies some nonlinear function, okay? So this architecture was given the name deep sets or point nets. So this is probably the most basic geometric deep learning instance. And again, you can see it as a special case of our blueprint. So in our case, the input is a set, right? So the symmetry is the permutation, so how I order the elements in the set. And then the function is permutation invariant, right? Obtained in this way. Okay? So it has been applied in applications, mainly in computer graphics, I would say this has become very prominent. So when you have point clouds, for example, you have a 3D scan of an object, you want to classify it or you want to segment it. So these architectures have become very widely used in the last probably 7 or 8 years. So the first architectures go back to 2017, and there are many versions of them. So you will see that it is a special case of graph neural networks where you have a trivial neighborhood. So that's what you need to know about deep sets. So basically, that's the first time we encounter permutation symmetry, permutation invariance and equivariance. You can see that you can obtain it in a very simple form. And you will see that basically we'll take these ideas and carry them on to graphs as well. Okay? So this is learning on sets. That's as easy as it gets, right? And from there it becomes slightly more complicated. Okay? Any questions? Well, I don't expect questions. I think it was very easy, right? So let's maybe move on to graphs. So that would be probably where more questions will be asked. Okay, so I think it's Ismail's turn now.